proceed with the session. So yesterday we looked at multiplexers and demultiplexers. We looked at their block diagram. We looked at some of their usages, their uses, and then we looked at their truth table also. But I think I forgot. Yesterday we left one thing out. We did not look at their logic circuit diagram. We didn't really look at their circuit diagram. So that was the only thing we left out yesterday. So I don't really want us to leave anything behind. Though that will mean we're able to finish everything early, but I really believe that even though you want to complete everything as early as possible, you want to make sure that we don't leave anything out. Okay, so I'm going to take the circuit diagram very fast and then we solve the question. So we are supposed to solve questions under multiplexers and demultiplexers before we move to encoders and decoders. So that is basically what we are going to do today. But before we start, please can see my it's my principle. Hello, hello. Please, am I audible?
Yes, sir. Hello.
Okay. But please, can you see my screen?
No, sir, we can't see your screen.
Oh, okay. Then let me cancel and share again. Okay. So please, is it showing now?
It's not showing, sir.
Please,
It's not showing, sir.
it's showing now, right?
Yeah, it's showing now. It's showing now.
It's showing now. Okay. So let's progress. Okay. So yesterday, oh, I don't know why are the rest not joining. It doesn't help. So let's continue. So yesterday we looked at what a multiplexer is, the various types of multiplexers, how to determine the input and output of a multiplexer, okay, and same for the multiplexer also. And another benefits, we said that it helps to reduce the number of connecting wires, it reduces the complexity of the logic circuit and reduces cost of implementing logic circuit, okay, since it reduces the complexity and makes the logic circuit more simpler. That means that the corresponding cost will be easier. And then the uses of multiplexer, it is used in telecommunication network and communication systems. And below is an example. So you can see the multiplexer here. And then there are four different devices that are connected to the multiplexer or that are sending
Please, we can't hear you if you're talking.
I'm sorry that we can't hear you. Hello, Mr. Isaac.
So sorry for that. My network just dropped suddenly. Okay. So please hope my screen is visible. Please, I hope my screen is visible now. Hello.
Yeah, hello. Please just finish. Just finish.
Okay, sir. Okay, sir. So I was trying to explain that there's a practical illustration of what we did yesterday. So we have four data lines. So data line 0 is an MP3 player. Data line 1 is a laptop. Data line 2 has been connected to a digital satellite. And then data line 3 has been connected to a digital cable. All these data lines are serving as inputs. And what are they? Which inputs are they sending through? They are all sending sound to just one sound system. Okay, so we have four different inputs and then just one sound system. That means that only one sound signal or only one sound feed can be forwarded to this particular sound system. And in order for us to know which particular device we should select for the sound system, we will need our selector. So the selector is going to tell us which particular device is going to be forwarded to the sound system. So if our selector is showing 00, if our selector is 00, that means data line 0 will be selected, which is our MP3 player. It means that as at that time, the sound we are going to be hearing in the speaker will come from our MP3 player. If 01 is showing on our selector, or if the selector selects zero, I mean, if our selector is 01, data line 1 will be selected, which is our laptop. So that means that the sound we are going to hear is going to come from our laptop. If 10 is selected, then that means that our digital satellite, the sound from our digital satellite is what we are going to be hearing in our sound system. And if our 11 is selected, that means that data line 3 is selected, which corresponds to our digital cable TV. So basically, this is how a multiplexer works. Okay, a demultiplexer is the opposite of a multiplexer. So we said that with a demultiplexer, you will have one input and many outputs. Okay, so that one you just have one input, and you want to know which particular output channel that input should be forwarded to. So that one also, we are going to do the same thing. We use a multiplexer, the selector, I mean the select line, to determine that. So if the selector is showing 00, it means that our input will be forwarded to output 0. Okay. If the selector is showing 01, it means our input will be forwarded to our output 1, etc. So that is how both works. Okay, so you can see this. You have your multiple data input, you have your selector or your multiplexer, and then the single data. So this is how a multiplexer basically works. So we established that yesterday, and we established the block diagram, the types of multiplexers, and then the truth table. So we said this is a 2:1 multiplexer. So if we have input A and input B, and then the corresponding output is Y, if our selector, which is X here, is showing 0, okay, then data line A will be selected, which is 0, right? So data line A will be selected. But if our selector is showing 1, or if our selector is line 1 will be selected, which is a B. The selector 0 will be selected, and if our selector is 1, data line 1. So that is, so what I omit our logical expression in a corresponding diagram. The logical expression for this one, we are going to take the inputs. I mean, we are going to, okay. So let's look at this. So in this scenario, we have our selector, right? Our selector in the first case, 0, S prime, right? And then our is 1, that is going to be X, right? And if selector is 0, data line 0, right? So data line 0 will be selected, which is A, and then is 1, which data line 1 will be selected.
Hello, sir. Please, your line is not very clear.
Yeah, it keeps breaking.
Okay.
We can't hear you. We can't hear you.
Please, you can.
Yeah, we can't hear Mr. Isaac.
Is that hear me? Or you can
It keeps breaking.
this is great. Sound okay now. Hello.
Yeah, we dey hear you.
Okay. So let's continue. Yes. I was explaining how to reduce a logical expression for okay. I was saying that the truth table multiplexer, you have your S0, right, and the corresponding data out. if your selector, your S, I mean, if your selector is 0, then data line 0 will be selected, right? And if your selector is 1, then data line 1 will be selected. So this was what we said. Oh,
You can't see your screen.
okay. You said you
Okay,
can
you
see
can
my
see,
screen, right?
Yeah, I can see now. Yeah, yeah.
Okay. So if your selector is 0, then data line 0 will be selected. And if your selector is 1, your data line 1 will be selected. So that was what we said yesterday. Okay. So in this case, you realize that when your input, you have data line 0, you have selector is 0, corresponding data line, you see, that is A. And A is 0, that is going to be X prime, right? If you write in terms of X, that is X prime, because let me leave that. And then if your please let me write that properly. So for your selector, our selector in this diagram here is X, right? In this block diagram here is X. So if our selector is 0, that corresponds to X prime, right? And if our selector is 1, that corresponds to X. And then the corresponding output is when our selector is S0, data line A is selected, or data line 0 is selected, which corresponds to A, which is 0. So 0 in terms of A, we can call it, so A will be selected, right? So if, how do you call it? If data line, if our selector is 0, our data line 0 will be selected, which is A. If our selector is 1, data line 1 will be selected, which corresponds to B. Okay. So you take the AND operation of both, which is your selector and then your data line. So you are going to get X prime A, which means that if your selector is 0, A will be selected. Or if your selector is 1, then B will be selected. The reason why your truth table is an OR operation is that only one output can be returned per time, okay? Because we said that a multiplexer has only one output. So that means that our final logic expression is going to be X prime A plus X B, okay? So you can proceed to draw the diagram for this. And our diagram is going to look like this. We said we have the X prime A. So here, they do this as a single input, which is X. And then you have the prime of that. So you have the NOT gates inverting the X. So that gives you X prime, okay? And so this is connected to this. You get X prime A, and then to the AND gates here, you get X prime B, okay? And then the two are joined together with an OR gate. And then you obtain the circuit diagram for the multiplexer. Please, I hope we are okay with this, or I should illustrate that for me.
Yeah, good.
Please come again.
We are okay. We are good.
All right, so we are going to use the same method for other types of multiplexers like 4:1, etc. Okay, so 4:1, we stated yesterday that it has two select lines, right? So S0 and then S1, right? And then the corresponding D output. So if you have S, your S is 0, your S0 is 0, your S1 is also 0, then data line 0 is going to be selected. So we said D0 will be selected. And then, so let's assume that, yeah, D0 will be selected. Let's just stick with that. And if your S is 0, here is 1, D1 will be selected. if you have 1 and 0, D2 will be selected. And then if you have 1 and 1, then D3 will be selected. Okay. So if you want to write the logical expression for this, for D0, we are going to get, if our S0 is, so we are going to get S0 prime, okay, and then S1 prime, because they are both 0, 0, then your D0 will be selected. But here, if S0 is 0, which is S0 prime, S0 prime, and then S1 is 1, so S1, then D1 will be selected. Then if S0, then S1 prime. S1 is 0, so prime or complement. Then D2 will be selected. And then 1, 1, which is if S0, if you have S0 and S1, then D3 will be selected. So just add everything. You add this to this to this, and then you obtain the logical expression for those. So assuming S0, assuming our S is let's say X and Y, okay, that's as S0 is X, our S1 is Y, and our D0 is, let's say, A. I mean, our D0 is A, our D1 is B, our D2 is C, our D3 is D. Then we are going to get something like S prime, Y prime, then A plus, we are going to get X prime, Y, and then B plus, we are going to get X, Y prime, then C plus, we are going to get X, Y, and D. So this right here is going to be the expression for it. And our expression for is 1. So to implement, we can that operation, product and that term here. To simplify this header if you want, okay. But to implement this, you are going to product term here. So I'm going to use we use gates and we combine everything together. All you have as the right. So have your but to I draw your okay. It's just as okay. Exactly. So really we proceed to a question. Okay, so let's move straight away to solving our questions. As our questions are loading, please, anyone have any questions? Please, do you have any questions so far? You have done and what you are doing? All right, so let's start with one. Okay, so we have our first question right here. So I think we start with this. Um, I think let's just continue from where we ended yesterday. So we did all
Yes.
this. Where did we get to? Did we start?
I think we got to question number 5. Please scroll down and let me see.
I didn't join.
Please scroll to question number 5. Let me see. 5, 6.
Number 6. Some someone question, what is a multiplexer? So A could put this one out. Means
Please, your line is breaking.
Your line is breaking.
Today, since your line is breaking, the line is.
What is happening?
It's breaking continuously.
Please, is it
Still can't hear you, sir.
now?
No, sir, your line is breaking. Yeah, I think you should leave and come again.
Okay. Please, is my sound better now? Hello.
Yeah, hello, sir.
Hi.
Okay. Please, is it okay now?
Yeah, it's
Yeah,
okay.
I think it's okay now.
Okay, all right. Then let's resume. So we are on the first question, and the first question is, what is a multiplexer? So it is a type of decoder which decodes several inputs and gives one output. B. A multiplexer is a device which converts many signals into one. C. It takes one input and results into many outputs. And D. It is a type of encoder which decodes several inputs and gives one output.
The answer is B. B.
B. Exactly, B is correct, because we said from the definition of a multiplexer and its behavior that it converts many input signals into one. So question 2, which combinational circuit is renowned for selecting a single input from many inputs and directing the binary information to output line? A. Data selector. B. Data distributor. C. Both data selector and data distributor. And D. Demultiplexer.
Data selector.
The answer is A. Data selector.
All right, so we have A as the correct answer, which is data selector. So question 3. It is possible for an enable or strobe inputs. I think this was the question I had a problem with yesterday. So it is possible for an enable or strobe inputs to undergo an expansion of 2 or more max ICs to the digital multiplexer with a proficiency of large number of, I think the answer to that was inputs. So let's go to question 4. Which is the major functioning responsibility of the multiplexing combinational circuit? So what is the major function of a multiplexer? A. Decoding the binary information. B. Generation of all minterms of an output function with OR gates. C. Generation of selected paths between multiple sources and a single destination. And D. Encoding of binary information.
I'll go for B.
All right, so we are going for generation of all minterms of an output function with OR
Yes, sir.
gates.
Yes, sir. Yes, sir.
So anyone else with another selection?
I second the B.
Okay, so we have A and then B, right? So I think I also go for a B, which is no. With question 4, I'll go for a C. That is generation of selected paths between multiple sources and a single destination, because I believe that better fits the definition and functionality of a multiplexer. But please, can you know why we are going for B? That is generation of all minterms in an output function with all gates.
Because when we look at the multiplexer, we said that we found a mean terms in it, and we use that mean term to generate an OR gate.
Okay, so we said that the finality of the operation of the expression of a multiplexer is the combination using an OR gate. Okay, so I think that is true, but if you look at the question is saying that what is the major, meaning that most of the things there can be functions, all right, or can be functioning responsibility of a multiplexer, all right. But then the question is asking for the major or the most important functionality of a multiplexer. And the most important functionality of a multiplexer is to ensure that multiple input channels are directed to one output channel. So that is the main functionality of a multiplexer. So if C is here, then I really think that we have to go for it, because it says that generation of selected paths between multiple sources and a single destination. And the part of a multiplexer that generates a path is a selector. So the selector forms, or is what dictates the path that data is going to take. I mean, with regards to routing data from an input to an output. So I believe C is correct, and that's true here. So let's look at the explanation. The major functioning responsibility of the multiplexing combinational circuit is generation of selected paths between multiple sources and a single destination, because it makes the circuit too flexible. A multiplexer or max is a device that selects one of several analog or digital input signals and forwards the selected input into a single line, depending on the active select lines. So please, I believe we all understand that. So let's go to 5. What is the function of an enable input on a multiplexer chip? Yes, A, to apply VCC, B, to connect ground, C, to activate the entire chip, and D, to activate one half of the chip.
C.
C, to activate the entire chip. Okay, so does someone else have another option in mind? So I'll personally also go for a C. I think when it comes to enable, we've not really talked about that. In fact, the slide hasn't really addressed the enable.
those enable.
But if you get to sequential circuits, we are going to really see how an enable input works. That's when you get to gated latches. Okay, when you get to gated latches, you will understand that an enable input is used to an enable input can be used to regulate an entire latch, an entire latch. Okay, so it functions more like a switch. If our enable input is 1, the entire circuit is on and is able to perform its function, and if it is off, the entire circuit is goes down or goes slow. So even if you apply inputs to it, the circuit is unable to function. So the function of an enable input, it is generic, okay, in all circuits, is that it activates the entire chip or the entire circuit. So if an enable input is low, the entire circuit is deactivated. Even if you apply input, it is not going to work. Okay, it is just like the on button of your television set. Okay, even if you plug the television set to a power supply and you turn it on, the television set is not going to work till you press the on button. So the on button functions as an enable input. Once the status is on, or once the status is high, which is 1, the entire television set goes on. And once the on button, okay, is low, which is 0, the entire television set will go off even if power is supplied. If you press any buttons or command on the remote control, it will not work. Okay, even though the switch is on until you've put the power button on. Okay, so that's basically how an enable input works. Okay, so let's read what is here. Enable input is used to activate the chip. When enable is high, the chip works, into brackets active. When enable is low, the chip does not work, into brackets memory. However, enable can be active high or active low, indicating it is active either when it is connected to VCC or GND respectively. Please, when you get to sequential circuits, we'll explain enable more, and we are going to understand how it works later. Okay, so don't worry. So question 6. One multiplexer can take the place of A, several SSI logic gates, B, combinational logic circuit. C, several XNOR gates. And D, several SSI logic gates or combinational logic circuits.
Combinational logic circuits.
Combinational logic circuit.
Okay. Okay, let's see what they have here. I think I'm not so familiar with this myself. The answer here is saying D. So a multiplexer or multi is a device that selects one of several input signals and forwards this to, depending on the active select line, since many operational behavior can be performed by using a multiplexer, whereas a combinational circuit is a combination of many logic gates, which makes the circuit more complex.
Oh, okay.
So I think that's better suits the characteristics of a multiplexer. That is, it helps simplify logic circuits. That we looked at. So it takes the place of several SSI logic gates or combinational logic circuits. All right. So let's go to question 7. So question 7. A digital multiplexer is a combinational circuit that selects A, one digital information from several sources and transmits the selected one. B, many digital information and converts them into one. C, many decimal inputs and transmits the selected information. And D, many decimal outputs and accepts the selected information.
A, one digital
Yes, I'll go for
information
A.
from several sources and transmits the
A.
selected.
Okay. So yeah. So one digital information from several sources and transmits the selected one. So I would also go for that. Yeah, so you are correct. So question 8. In a multiplexer, the selection of a particular input line is controlled by A, data controller, B, select line, C, logic gates, and D, both data controller and selected lines.
I'll go for D, both data controller and selected lines.
Exactly.
Okay, all right. So I'll go for B. Okay, I'll go for B here, which is select line, because the selection of a particular input line is always controlled by the selector. So we said that the selector input is the only thing that determines which particular input line can be selected. Yeah, so select line. So the selection of a particular input line is controlled by a set of selected lines or select lines in a multiplexer, which helps to select a particular input from several sources. So please let's take note. So it is a job of a or function, though data controller sounds solid, but in a multiplexer, it is the sole job of our select lines to ensure that one particular input is selected and sent to our output. So please let's take note of that. So question 9. If the number of n selected input lines is equal to 2 power n, then it requires, please let's look at this question carefully. If the number of n select lines is equal to 2 power m, then it requires dash select lines. Okay, so we have our input is 2 raised to the power n. How many select lines will be needed? A, 2, B, n, C, n, and D, 2n.
D, 2 raised to the power n.
Okay, so anyone with another answer in
M.
mind? Please come again.
M.
M or N? Please, are you referring to B
M.
or C?
B.
That's B. Okay. So I would also agree with B, because you said that for a selector, for a multiplexer, 2 raised to the power your inputs will give you your no, 2 raised to the power your select lines, I mean, will give you a number of inputs. So let's illustrate that here. So we said that 2 to the power select lines, right? Number of select lines will give you your inputs. Okay, so if the question is saying that our output is 2 raised to the power n, our input is 2 raised to the power n, how many select lines are there? It is n. Please, can you see that?
Is it M or N
M.
from
M,
the question?
M.
M.
Yeah, the question is n. Yes, please. So that's 2 raised to the power n. Please, do we understand that? So we derive this from the expression, okay, for a multiplexer. That is when we are deducing the number of inputs. We said that the number of inputs is equal to 2 raised to the power n, or 2 raised to the power n, okay, in the original formula, where n is our number of select lines. So in the question, we said that the number of inputs is 2 raised to the power n, okay? So we can write this mathematically as 2 raised to the power n is equal to inputs. So 2 raised to the power n is equal to inputs, okay? So now we know that our n here, this our n here, is equal to our select lines, okay? Because you know that in the original formula, 2 raised to the power, your select lines will give you the number of inputs. So if the select line is 2, your number of inputs will be 4. If your select line is 3, your number of inputs will be 8. Please do recall, if your select line is 4, your number of inputs will be 16. So it means that our power is our select lines. So here our power is n. So we can say that n here is our select lines. Please, are we okay with that? Well, please, can we move on?
Yes, we can move on.
All right, so let's go to question 10. So question 10 is saying that how many select lines will be required for an 8-to-1 line multiplexer? How many select lines will be required for an 8-to-1 line multiplexer? Okay, so we have an 8:1 multiplexer. How many select lines are you going to need?
4.
3.
All right, so we have
Yeah,
8:1. Someone said 3, someone said 4. Okay. So anyone again with another answer? So please, who said 3?
I was the one who said 3.
Okay, that's Mr. Nyankun. Right. So
Yeah,
I think
3.
Mr. Nyankun is right. So 3 is correct. Because you said 2 raised to the power, our select lines will give us the input, right? So 2, we know 2 raised to the power 3 is what will give us 8. Okay, so 3 is our number of select lines. Okay, so we stated that, yes, sir.
Please, what about the 2:1 multiplexer? Do you need 4?
2:1 multiplexer. Our select lines is 1. Okay, because you know 2 raised to the power n is going to be our input. And the input for a 2:1 multiplexer is 2, right? So 2 raised to the power
So
4
4.
will give you, it's 1.
So 4.
No.
Hey.
No, 2 raised to the power 1 will give us 2.
Give us 2, yes.
Exactly. So that means you need 1 select lines. Okay, so that means that, let me establish a relationship directly and simply, okay, simpler. So for a 2:1 select line, a 2:1 multiplexer, you need 1 select line. For a 4:1 multiplexer, you need 2 select lines. For an 8:1 multiplexer, you need 3 select lines. For a 16:1 multiplexer, you need 4 select lines. for a 32:1 multiplexer, we need how many select lines? 5. It's very good. And all of them, if we take 2 to the power 1, we'll get what? 2. 2 to the power 2, we'll get what? 4. 2 to the power 3, we'll get 8. 2 to the power 4, 16. 2 to the power 5, 32. So please, I believe we've seen that now. So Mr. Nyakun is right. The correct answer for that is B, which is correct. So question 11. A basic multiplexer principle can be demonstrated through the use of a single pole relay, B, DP/DT switch, C, rotary switch, and D, linear stepper.
Yeah, look to show. I think A. This question, this is my first time, but I'll go for A.
Okay, so single pole relay. All right, so we have DP/DT switch, rotary switch, and linear stepper. Okay, so I'm going to go for C. So let's do a simple research here and then see something. All right, so this is what a rotary switch is. Let's look at this. A rotary switch is an electromechanical device that controls multiple circuits. Okay, so it controls multiple circuits or positions using a rotary knob or spindle, acting as a versatile alternative to push button switches. They are defined by their ability to click into specific positions ranging from 2 to over 50 to select functions and applications like industry machines, audio equipment, and appliance control. All right, so rotary switches here is the closest to a multiplexer. So if you are to look for devices that employs same logic as a multiplexer, you see that the rotary switches are one of them. So they function by selecting several inputs. Okay, so you have several inputs connected to it, and then it selects one of the inputs as output, or you have several devices or equipment selected to it. Some of the equipment can be machineries, can be audio equipment, and then appliances. Okay, and they are used to, select whichever ones is suitable for outputs, etc. So a rotary switch, I believe, is the best option for this. Honestly, some of the options like DP/DT switch and then linear step, I don't know what they are. All right, so that is it. So let's go to question 12. How many NOT gates are required to construct a 4:1 multiplexer? How many NOT gates are required to construct a 4:1 multiplexer?
2.
Okay, so we all agree with 2, right?
Yeah.
Okay. All right, so 4:1 multiplexer. Let's see. So we said 4:1 multiplexer, we have 2 selectors, right? S0, S1, we have our output as, we already illustrated it, but for understanding purposes. So here, let's use D, okay? And D can be A, B, C, D. And then S, our selector are labeled X, okay? So we have 0, 0, right? So 0, 0 will be X prime. Let me see. X prime, X prime, okay. So, no, I'm coming. Let's use S prime and Y, else I'll have to use S and x0 instead, or x0 and x1 instead. So let's use y for s1. So y prime. And then 0, 1, we are going to get x prime y. And then 0, 1, 0. That's 1. We are going to have x0, we have y prime. And then last one, we have 1, 1. We are going to have x and y. Exactly. So here you are going to have A, you are going to have B, you have C, and you have D. So you are going to have x prime, y prime times C, right? Plus, here you have, no, times A.
Yes, times A.
Right. And you are going to have x prime, y times B plus x y prime times C plus x y times D, right? So to implement this, here you are going to have our A, B, C, D, which is our select lines as our input, right? So we have our A right here. We have our, no, our X and Y are select lines, not A and B. Okay. So let's do that properly. So we have X, and then we have Y, right? And then with our X and Y, you know, we have to take the knots of X also, because we have X naught, Y naught, right? In it, so we have the knots of X, and then the knots of Y. Right here, right? Yeah, so yeah, so I think I agree with you. So basically, the main knots that we are going to use to implement this are going to be X knots and Y knots. Okay, because if you check for A, B, C, and D, we have no knots right there. Okay, so I think I would agree with 2, because the basic number of knots that we are going to use to implement this, node gates that we are going to use to implement this, is an X knot and then a Y knot, which is just 2. Okay. So aside this, if you check all the corresponding inputs, which is A, B, and C, D, they have no knots, so we don't need to represent the knots of any of them. So we can just pause there and then go for our C. So I would also agree with a C. Exactly. So you can see that in the diagram there. Okay. So I think they use C1 and C0 as their select lines, but we use X1 and then X0. And you can see they use X0, X1, X2, and X3 as their inputs, but we use A, B, C, D. And you can see that the knots that we use, or the knots gates that we use, were just 2, which was C1 knot and C0 knot, which corresponds to our X naught and then our Y naught. Hence, 2 is the correct answer. So question 13. In the given 4-to-1 multiplexer, if C1 equals 0 and C0 equals 1, then the output M is, I think this let's all do it together. So please, everyone should attend this question. So we have a given 4-to-1 multiplexer. C1 and C0 are our select lines. So C1 is actually 1 and C1 is actually 0 and C0 is 1. So the output N is going to be A, X0, B, X1, C, X2, and D, X3. What are we going for?
X1, B.
Okay. So that's Mr. Nyako, right?
Yes, please.
All right, so Mr. Nyako is going for B, which is X1. Yes. Joshua, would you want to select something?
Yeah, I'm checking. I'm looking through.
Okay. Oh, what did I click on?
And maybe I think you should refresh it.
Okay, so I think we are yeah.
I think I'll go for X1.
Yeah, so it's
But you go
X1
for what?
because 0, 1 is simply
Yes, I'll go for X1.
1 in binary numbers, so X1.
Yes, X1, B. I'll go for B.
Okay. So I'll also go for B because we said that our selector is showing 0, 1. And you know that 0, 0 corresponds to data line 0, which here is X0. And 0, 1 will correspond to data line 1, which is X1. So there is even no need to maybe try to trace the entire diagram to determine N. Once you know your select line is 0, 1, you know is data line 2, which is X1. So that is the explanation. The output will be X1 because 0, 1 resolves into 1, which further resolves as S1. Okay. And rest of the AND gate gives output as 0. So our X1 is our correct answer. So the enable input is also known as, I think you have a question on the enable again. So the enable input is also known as
Select input.
I'm like, no. We said the enable input is a universal switch. It's either turns the entire circuit off or on, or it sends it either low or high. So please, another name for the enable inputs. The enable is very different from the selector. That one is functions like a switch to the entire circuit. Exactly. It's also
Then a
called a
strobe.
strobe. Exactly. It's also called a strobe. So please let's just take note of it. And this one is even easy to identify because that's the oldest option out. If you look at select input, you know it's wrong. A select input is a selector. Decoded input. And an enable input is not a decoded input. Okay. So a sync is, I mean, doesn't make sense. So you know strobe is even most likely the correct. So we have our C, which is our strobe being correct. All right, so we are done with part 1 of our multiplexers, our questions. Let's go to, oh, come on. So let's go to the second part and complete everything under that. All right, so we have our part 2, right? And our multiplexers. So question 1, a 4-to-1 multiplexers will have A, 2 inputs, B, 3 inputs, C, 4 inputs, and D, 5 inputs.
I'll go with
Two
B.
inputs. Two
Yeah, so
inputs.
A.
Please come again.
Two inputs.
Yeah, A.
Okay, please. Joshua, you went for 2. Mr.
Four,
Nyaku, you
four
also
inputs.
went for
Four.
2.
Two input.
I'm going with 4.
Okay,
I'm
going
going
Mr.
with
Nyaku, you
2.
are selecting 4.
No, I'm picking two.
Prince,
Two
Prince
input.
is
You are picking 2. Okay, so someone said 4. Who is going for 4?
Prince.
Mr.
All right,
Waji.
Mr. Abuaji is going for 4. Okay. Joshua, you're also going for 2.
Yeah, I
Okay.
went for 2.
You are going
Two,
for
two.
2. Okay. Interesting enough, Mr. Abuaji is correct. It's 4. We said that a multiplexer, the type of multiplexer is defined by the ratio of the input to output. So a 2:1 multiplexer is 2 input, 1 output. 4:1, 4 input, 1 output. 8:1, 8 input, 1 output. 16:1, 16 input, 1 output. Please, a 4:1 would rather have 2 selectors, not 2 inputs. Please take note, selectors are different from input. Okay, input, we are talking about our D. That's D0, D1, D2, D3, D4, etc. Okay, so let's distinguish the difference between a selector and then our inputs. Okay, so a 4:1 max will have 4 inputs, which is D0, D1, D2, and then D3. And then 1 output, which is going to be our Y0. So please, the correct answer is 4 inputs. If they were to ask for the number of select lines, we would have gone for 2. Okay, but they ask for input, it is 4. So you can see that the correct answer is 4 inputs. So question 2, the 2 inputs max would have, so a 2 input multiplexer will have A, 1 select line, B, 2 select lines, C, 4 select lines, and D, 3 select lines.
One select line. So I'll go for one select line.
All right. So 1 select line, we are correct. But we said that a 2:1 multiplexer has 2 inputs and 1 select line. Okay, because 2 raised to the power the number of select lines gives us the input. In this case, 2 raised to the power 1 gives us the inputs, which is 2. So 1 is our number of select lines. Question 3. A combinational circuit that selects 1 from many inputs are a combinational circuit that selects 1 from many inputs are so many to 1,
multiplexer.
many inputs. 1 is a multiplexer. So let's move on. Question 4. 4:1 max would have A, 1 output, B, 2 outputs, C, 3 output, D, 4 outputs.
4 output.
One out.
Two
One
output.
out.
One out.
2 out.
All right, so let's
One out.
see. Who is going for 1?
Yeah. One.
Go for.
Exactly.
I'm going for
1
So
output.
1 is correct because you said that 4 is the input, 1 is the output. When you are dealing with multiplexers, the outputs are always 1, irrespective of the number of inputs you have. And the opposite is true for demultiplexers. The input is rather always 1, no matter the number of outputs you have. Okay. So multiplexers have only 1 output, demultiplexers have only 1 input by many outputs. So multiplexers is many to 1, demultiplexers is 1 to many. So question 5, which of the following circuits can be used as parallel to a serial converter? Which of the following circuits can be used as parallel to a serial converter? Honestly, I'm not familiar with the structure of this question.
Demultiplexer.
Please come again.
B, demultiplexer.
Okay. So anyone with another option? Okay, so let's see the answer. All right, so we have A, multiplexer. And the explanation is that a combinational circuit that selects one from many inputs is known as multiplexer. In multiplexer, different inputs are inserted parallelly, okay, and then it gives one output, which is in serial form. I think this is quite technical and very, very technical. So question 6, a combinational circuit is one, but please, let's just take a note, okay, of that. So question 6, a combinational circuit is one in which the output depends on A, input combination at a time, B, input combination and the previous output, C, input combination at the time and the previous input combination, and D, present output and the previous output.
Input combination at a time.
The previous
Exactly.
outputs.
Combinational is only the input combination. So input combination at a time. Question 7. Without any additional circuitry, an 8:1 max can be used to obtain. Please, let's take note of the question. Without any additional circuitry, an 8:1 max can be used to obtain A, some but not all Boolean functions of 3 variables. B, all functions of 3 variables, but not of 4 variables. C, all functions of 3 variables, and some but not all of 4 variables. And D, all functions of 4 variables. I think, please,
It's A.
All functions of all variables.
I'm in for A.
okay, so
D. I'm saying
D.
D. Going to say D.
Okay. So I think D is correct. We didn't talk about implementation of that's one of the functions of a multiplexer, and it just remains as a function. Okay, it can be used to implement Boolean expressions as well. Decoders can also do same. So let me illustrate how this works. So assuming you have a multiplexer, okay, this is an 8:1 max. So let's call this whatsoever. So we have an 8:1 max. Okay. So this 8:1 max can be used to implement a 4 variable Boolean expression. Okay. Etc. Etc. So you can just use the simple method of using 2 raised to the power your select lines plus 1. Okay. To know the number of variable Boolean expression that this can implement. I think when we go to encoders and decoders, we'll talk much more about implementing a Boolean expression using any of the circuits. Okay, and then you highlight that better. Okay, because it has its own logic gates, etc. I mean, truth table, etc. So you look at that when we get there. When we get to encoders and decoders. Okay. A basic multiplexer principle can be demonstrated through the use of a. Oh, I think we've already looked at it. So, what is the answer for this? So we have single pole relay.
That's C.
I'll go with C.
Yes, a rotary switch is correct. Now which question? Now which question, please?
Question 9. But it's also a repeated question.
Oh, okay. So question 10. The input or output of an analog multiplexer or demultiplexer are A, bidirectional, B, unidirectional, C, even parity, and then D, we have what do we have? Binary coded decimal.
D. Binary coded decimal.
Okay, so yes. So we are going for D, right? Let's look at the correct answer. All right, so we have A, bidirectional. And the explanation is that one multiplexer can be used as demultiplexer. Hence, it is called bidirectional or two-way transmission. All right, so we know that a multiplexer is the opposite of a demultiplexer, right? So you can invert a multiplexer, you get a demultiplexer. So bidirectional, meaning one multiplexer can be inverted and used as a demultiplexer. Because if you invert a 1:4 multiplexer, you get a 4. If you invert a 4:1 multiplexer, you get a 1:4. If you invert a 1:4 multiplexer, you get a 4:1 demultiplexer, right? So let's look at question 11. So if enable input is high, then the multiplexer is, yes.
Yeah, I'm sorry to cut you off. I joined late, so I didn't know the answer for number 9.
Oh, okay. Okay, so number 9, one multiplexer can take the place of A, several SSI logic gates, B, combinational logic circuit, C, several XNOR gates, and D, several SSI logic gates or combinational logic gates, as combinational logic circuits. So please can someone tell us the answer, please?
The answer is D. Several SSI logic gates or combinational logic gates. A circuit.
Exactly. So we went for D as the correct answer, and our explanation is that one multiplexer can take the place of several SSI logic gates or combinational logic circuit because it has a lot of functions to perform different operations. Okay. So when we're looking at the uses of multiplexers, one of the uses is that it helps simplify logic circuits. Okay. So one of its functions is the simplification of logic circuits. So in this case, we go for D. It can be used in place of, instead of using several logic gates, you can rather use a multiplexer, which rather simplifies the circuit. So question 10. Oh, we looked at question 10, right? So it's a bidirectional. 11. If enable input is high, then the multiplexer is A, enable, B, disable, C, saturation, and D, high impedance. Yes, I think for this, you should be able to know the answer for this.
Enable.
A.
Yeah, it's enable. Exactly. So we said that if the enable input of a multiplexer is showing as 1, it means the multiplexer is currently high. So question 12, what is data routing in a multiplexer? What is data routing in a multiplexer? What is
This is
data
to
routing in a multiplexer? Okay.
route data from one of several source to destination. Or B.
All right. So all right. So you have data routing in a multiplexer. So it is used to route data from one source, okay, to its destination. And the device in a multiplexer that handles that, or the logic in a multiplexer that handles that is our selector. We already established that, right? That it basically determines which input is routed or which data is routed to our outputs. All right, so it selects one data line and then routes it to our output. All right, so we are done with this part, shall we? I'm feeling very sleepy. Let's just finish with the third part and then. All right, so demultiplexers. Hey, demultiplexers, we are one and two. Let's finish with this. Let's finish with this. So question 1. The word demultiplexer means A, 1 to many, B, many to 1, C, distributor, and D, 1 into many as well as distributor. Yes, I think we all should be able to get this.
So the answer is
Many to 1.
D makes sense. Oh.
Can you tell us why this makes sense? So you're
I
not
heard
talking
you
about
saying.
multiplexer. You're
I
talking
I
about
heard you saying.
demultiplexer.
Yes, I heard you
You
saying we have many to 1 and 1 to many for demultiplexer and multiplexer.
Yeah, I'll go with A.
So I'll go with A.
So you go with A.
Yes, for
no,
Phoenix.
I'll pick B. I'll pick B.
B
Many to
B
one,
many into 1.
many to one. But at the same time, demultiplexers, they are distributors too.
Okay, so let's look at something here and clarify the answer. Okay. And I think the main way here is understanding the difference between a multi. So we said that a multiplexer, you have many inputs to one, right? And it functions as a selector. Okay. So it selects one input and then routes it. It selects one data line and then routes it to one output, right? Now this is a, please forgive me. So this is a Demux rather. This is a max, sorry. This is a max. And let's take a Dmax. So a Dmax will take one input and then route it out to several output channels, right? So we have D0, D1, D2, D3, or you can use Y indicating our output, okay? So let's say Y is our input, and then you have two select lines. So this is a demultiplexer, this is a multiplexer. So let's look at how multiplexer functions. So it first takes one input, which is 1, and then sends it out to many outputs, right? Many output lines. So 1 to many, okay. And then since it takes one input and then distributes it to several output channels. Yeah, we can tag this as a data distributor, which is very accurate and correctly depicts the functionality of a demultiplexer. Okay, so multiplexer functions more like a data selector. Okay, but a demultiplexer will function as a data distributor. So I think I would side with Mr. Nyako option D. All right, so please do we all agree on that? All right, so D, we have D, which is one into many, as well as a distributor. Please, any question on that? Please, any question on that? All right, so question 2. Why is a demultiplexer called a data distributor? A, the input will be distributed. I think we've already discussed this. The input will be distributed to one of the outputs. B, one of the inputs will be selected for the output. C, the output will be distributed to one of the inputs. And D, single input to single output. Yeah, so which one are you going for?
A.
Okay.
Yeah,
So please, do you all agree on A?
yes.
So
Yes.
you realize that A is very close to B. Okay. But the main difference is selected and distributed. Let's just take note. We said that a multiplexer selects, we have many inputs, so a multiplexer will select one input and then route it to the corresponding output medium or the corresponding output channel. But then a demultiplexer will distribute one input to the corresponding output channel. Okay, so the input will be distributed to one of the output channels. So A is correct at this place. Yeah. So let's go to question 3. Most demultiplexers facilitate which type of conversion? Most demultiplexers facilitate which type of conversions? A, decimal to hexadecimal. B, single input, multiple outputs. C, AC to DC. And D, odd parity to even parity.
B.
B is correct. Single
I would
input,
go with B.
many outputs. From A, C, and D, you are talking about decoders and encoders. Okay. So decimal to hexadecimal, AC to DC, odd parity to even parity, you are dealing with encoders and decoders. They tackle those conversions? Okay, not multiplexer. Okay, or demultiplexer. So question 4. In 1 to 4 demultiplexer, how many select lines are required? A, 2, B, 3, C, 4, and D, 5. Yes.
A. 2.
Come in. 2, right? All right, so 2 is correct, right? Okay. So we use 2 raised to the power n, right? And then in this case, will give us our output. So in this case, 2 raised to the power 2 will give us our output, or you can take our output and take the square root of it. You'll get our corresponding input, which is 2. So question 5, in a multiplexer, the output determines on A, data inputs, B, select inputs, C, select outputs, and D, enable pin. B. Who is Joshua? Is that you? Please, who went for the B? Is it Mr. Joshua? Please, who is
No,
going
sir.
for B?
No, sir.
Yes.
Please, what question? Number 6.
Please come again.
Please, what question?
Okay, you have a question.
I said, please, what question number?
We're on question number 5. In a multiplexer, the output depends on it. And I think I heard someone say select inputs. So I'm just figuring out who said that. Okay, so select input is correct.
Yes, sir.
Because we said that our selectors is what determines the particular output will be selected. Or our input will be distributed to. It is our select count which determines that. So question 6. In 1 to 4 multiplexer, if C equals 1 and C2 equals 1, then the output will be. Let's look at this question. In a 1 to 4 multiplexer, if C equals 0 and C2 equals 1, C1 equals 0, C2 equals 1, then the output will be A, Y0, B, Y1, C, Y2, and D, Y3.
I'll go with B.
D.
All right, so I think I heard B and then I heard D also. So let's just look at. Okay, so let's just look at that. So we have Y0, Y1, Y2, we have Y3. Our selector is 1, 1. What will be our output? So you know 1, 1 corresponds to 3, right? So we have our data line 3. So this is our data line 1. So we are going to have data line 0, line 1, line 2, line 3, which will correspond to our Y3. So our output is going to be our Y3. Please, if you all get that. So that's going to be D, Y3. So question 7. In a 1 is to 4 multiplexer. I think the question
Please, besides it,
is
I think it's a different question because like that one is 1 and 0.
Please, the 6 is 0. Okay, the 6 is 0 and 1. Oh, okay, I was looking at this right here. And even the question is not a demultiplexer, it's a multiplexer. Okay. So the question 6 is saying in a 1 to 4 multiplexer, C1 is 0, C2 is 1. Okay, let's do that. Okay. So we have our inputs as Y0, Y1, Y2, Y3, right? So we have 0 and then 1. So that's going to be data line. That's going to be Y0. Because 0, no, Y1. What's wrong? So that's going to be Y1 because you have 0, 1, right? 0, 1, 1 corresponds to data line 1. Okay. And here is data line 0, here is data line 1, which is Y1. Please, do you all agree with that? So please, do you all agree with that?
Yes, sir.
Okay. And then the question 7, that is 1, 1. 1, 1 will correspond to data line 3, right? So you have data line 0, data line 1, data line 2, data line 3 is Y3. So that's going to be option D. Okay. So let's go to question 8. How many select lines are required for a 1 to 8 demultiplexer? Yes.
Three.
All right, so 3 select lines is correct because 2 is a power 3 is 8. How many AND gates are required for a 1 to 8 multiplexer? I think even the answer is in the next question, Cram. So how many AND gates are required for a 1 to 8 multiplexer? So we have
8.
1, 2, 3, 4, 5, 6, 7. Okay, 1, 2, 3, 4, 5, 6, 7, 8. So 8 is correct. So 8 right there. And I think if we draw a truth table, each of the expressions for D0, D1 up to D7, they will all be a product of a sum of product expression. And we know sum of products will always be represented using an AND gate, right? So literally, the first product term we use an AND gate, second product term AND gate, and we have 8 different product terms for D0, D1, D2, D3, up to D7. And then each is going to be implemented using an AND gate. And this one, there is no need. Please, can someone tell me why we didn't join everything together using an OR gate? Please, does anyone know why? Realize that when we're talking about multiplexer, when you draw the circuit, you join or you connect everything together using an OR gate. But here, you realize that the AND gates were not connected together with an OR gate or any other gate. Please, anyone knows why? All right, so let me just state the reason why. The reason is because when it comes to a demultiplexer, it rather routes one input to one output medium, okay? So to many output medium. All right, so what happens is that you literally do not have just one option for outputs. So when it comes to outputs, the options are going to be multiple. If you have to join or connect all the 8 AND gates together, it's like you are trying to say that one way or the other, all those outputs are interlinked, or one of those outputs will be selected. I mean, connected, something like that, which is not true. All right, so let's go to the next question. Please, when you are done with this, please, you are done. I can see people are tired myself. I'm feeling very sleepy. So question 10, the output of Q4 of this 1 to 8 demultiplexer is. So the output of Q4. So we cannot see Q4. That's data line 4. Is going to be what? Let's see the options. All right, so we have Q2 dot Q1 prime, Q0, etc., etc. So I think we can easily illustrate this, right? On an NC sheet. So let's illustrate this. So we have 3 select lines. So S0, S1, L1, 1, 0, 0, 51, D3, and then about D4, right? D4, we have 1, 1, 0. So D4 is what? S0 complements S1 complements S, and then our D4. So So let's check which one corresponds to that. Okay. So complements. All right, so I'll go for C. Please, do you all agree with that? Hello.
It's a bit confused.
It's a bit confusing now. Okay. So let's first see. Yes, C is correct. Okay. So you see, the question said that just forget the diagram. The question said that the output Q4 of a 1 to 8 multiplexer is. So you are looking for, and they gave 4 expressions. You are looking for Q4. Okay. So you draw your truth table. You have, you know that a 1 is to 8 demultiplexer will have 3 select lines, right? Your 3 select lines are S0, S1, and then S2. So if you draw your input combination, you are going to have S2 being 0, 1, 0, 1, 0. You are going to have S1 being 0, 0, 1, 1, 0. You have S0 being 1, 1, 1, 1, 0. The reason why I ended here is that this particular combination corresponds to Q4. You can see that this one takes D0, okay? So in that is a set Q, so you have Q0, Q1, Q2, Q3, and here will be Q4, okay? So what is the expression for Q4? You see that S0 is 0, so you have S0 complement. S1 is 0, so you have S1 complement. S2 is 1, so you have S, and then you have D4. So it means that they express the final answer in terms of Q and I, right? So let's do just that. So S0 is Q, so we have Q complements, we have Q1 complements, and then we have what? I. And then that will give us what? D4. So let's check. You can see that we have the first complements, we have our second complement, and then we have our I. Hence, the C is the correct option. Okay, so we have our last question. Which IC is used for the implementation of a 1 to 16 Demux? I'm not sure of that myself. So this is IC 74154, which corresponds to A. Okay, it's used to implement a 1 to 16 demultiplexer. All right, so I think we'll end tonight's meeting here. There is one more quiz on demultiplexer, which is quiz number 2. So please, if God willing, tomorrow, try and take it yourself. So now we are done with multiplexers and demultiplexers, so we can move forward to finish decoders and encoders so that you can quickly switch to sequential circuits. All right, so let's meet tomorrow.